Hey everyone, today we are diving into 6 powerful numerical methods in Python for finding the roots of equation, the points where your function hits zero. Whether you're a student, a programmer, I'll walk you through each method step by step. So let's get started. First method is the graphical method. The graphical method is the simplest root finding technique. We evaluate the function of a range of x values using numpy.linspace and get the values of y. When they loop through each pair of points, if there's a sign change between two f of x values, we estimate a root at the midpoint of those x values. We start by sampling 400 points evenly in the given range using np.linspace. We evaluate the function at each of these points. We look for assigned changes between two consecutive y values, a key sign that a root lies between them. We estimate the root as the midpoint between the two x values. I also prepare iterations for output, which just log the x and f of x values. This method doesn't guarantee exact roots, but it's perfect for visualization and estimating where roots might be. The second method is the incremental search. This method starts from a given x start and move in step. Default is 0.1. At each step, it evaluates f of x and checks if the sign of the function changes between 2 points. That's where a root is likely hiding. This method steps through the range using a fixed increment, delta. For every small interval, we check if there are signs between changes f of x and f x plus delta. If a root is detected, we approximate it at the midpoint. Approximate the root at the midpoint between the two x values. Each log in roots and every step is recorded in iteration. We stop when we reach the end of the range or hit the max number of steps. This is likely more precise than graphical because it's actively stepping through the domain. The third method is called bisection method. The bisection method is a reliable and powerful root finding method. It requires that f of a and f of b have opposite signs, meaning the function crosses zero in that interval. Then we find the midpoint c equals a plus b slash 2 and check the value f of c. If f of c is close enough to 0 or the interval is small, we consider c as a root. Depending on the sign of f of c, we either move a or b closer to the root. Each iteration is logged with a, b, c, and f of c, and we repeat until we reach the desired tolerance or max iteration. It's slow but very accurate if the initial interval is valid. We assume the root is between a and b, and we cut this interval in half iterative. The fourth method is called regular falsi method. Regular falsi, or the false position method, is a smarter twist on bisection. Instead of using the midpoint, it uses a linear interpolation to estimate the root. So c equals b minus f of b times b minus a slash f b minus f of a. This typically converges faster than bisection, especially when the function is nearly linear near the root. We still check if f of c is close to a zero, and adjust a or b based on the sign of f of c. Each step is stored with the current interval and the guess is c. Just like bisection method, this method works well when f of a and f of b have opposite signs. Instead of just using the midpoint, regular falsi uses the intersection of the second line between a and b. As with bisection, we stop if our estimate is accurate enough. The fifth method is called Newton-Raphson method. The Newton-Raphson method is fast and powerful, but requires the derivative of the function. We start with an initial guess of the midpoint of the interval, then we compute x1 equals x0 minus f of x0 slash f of x0. This formula uses the tangent line at x0 to estimate where the function crosses 0. We repeat this process until the difference between guesses is smaller than our tolerance. Each iteration lags x0, f of x0, then derivative of f x0, and the new guess x1. This method converges very quickly, but can fail if the derivative is 0 or the function is poorly behaved. This method uses the tangent line at the current point to jump to the next approximation. If the guess stop changing significantly, we've likely found the root. The last method is called second method. The second method is likely Newton-Raphson but without needing a derivative. It starts with the two initial guesses, x0 and x1, and uses the second line between them to estimate the root. x2 equals x1 minus f of x1 times x1 minus x0 slash f of x1 minus f of x0. We update the guesses and repeat. Each iteration lags the previous value and the new one, and we stop the guess changes by less than our tolerance. This method is faster than bisection and doesn't need calculus, a great trade-off between speed and simplicity. The second method is likely Newton-Raphson, but instead of using a derivative, it approximates it with two prior points. Same logic, we stop when our guesses stabilizes. And that's all 6 methods. Each has its strength: graphical for intuition, bisection and regular falsi for safety, and Newton and second for speed. That's all the 6 methods.